we're very lucky to have Ron with us for over the last couple of years. And one of the things that I think that Ron provides is I'm a great believer of cross-fertilization of information. And I don't mean that in the biblical sense, but what tends to happen in Scotland is that we can be a bit isolated because we're far away from the main centres of gliding down south. And Ron, with his experience, in gliding both within the BGA and flying at Bicester. Now, Bicester has always been a centre of excellence, particularly from the thermal cross-country point of view. And that leads on to the McCready, because thermal soaring in Scotland isn't that easy, which is one of the reasons that we're doing things like, encouraging learning to soar down, learning to do thermal soaring down south so that you can apply it up here, because it is actually quite difficult to thermal soar up here. And one of the things about that is this is where the McCready comes in, because the important thing is people tend to dally too much at the top of the thermal, which really you lose time, because it's all about time, maximizing the day. And that's where the McCready comes in. And as I say, Ron's really quite an expert at it, and is going to sort of illuminate us as to how we can get the best out of it, because it'll make us better cross-country pilots. I mean, I've been flying all my life, and and I'm really interested in listening to this as well. So without further ado, over to Ron.
Thank you, Sam. Good evening, everyone. Welcome to the short but hopefully informative presentation on McCready. It's all about the optimum speed to fly. Now, we're going to start with, like we do on every flight, threat and error management. This presentation may contain a bit of mild humour. We'll come on to that in a bit. So just make sure you don't spill your drinks or choke on your snacks. It may also contain facts and evoke questions. And as Martin said earlier, put your hand up, we'll get the mic to you, and you can ask your question, and we'll just stop the proceedings until we've answered that. There is a disclaimer, and that is I've had to choose a couple of names to go with a couple of gliders so that I can talk about pilots in particular. Now, I didn't want to choose any particular club member, so I've chosen names at random. And I did this by setting up my Scrabble boards and then just turning letters over, and I came up with Alistair and Sant. Well, that was completely at random, so the disclaimer refers, okay? In the interests of accuracy and correctness, all comparisons that I'm going to make tonight must be taken under the context that you're flying exactly the same air mass. So if I'm talking about two gliders flying from A to B to C, okay, they are in exactly the same air mass. There is no differences between the two of them in that respect. There's also been a few rumours going around that I've heard, certainly. I came across someone talking about McCready saying that you could fly faster than McCready. I went away and did the maths, and no, you can't. But we'll review this at the end, and we'll discuss it if need be. So anyway, let's crack on. I'm hoping that you'll learn some new facts about McCready. The first one, which some of you might not know, is his first name's Paul. So there's your first fact. That's your starter for 10. He first described the optimum speed to fly selector back in 1954, I believe. And my aim today or tonight is to hopefully give you guys an insight into the usefulness of McCready and give you an understanding of its importance in cross-country flying. So, to make use of McCready, we're going to require some tools in the cockpit. And the first tool that we're going to need is a McCready ring. This is the old-fashioned way. The McCready ring is attached to your variometer, and it looks something like so. We'll come back onto the McCready ring and how to use it in a little while. There is a more modern way of doing things, and that's with the more modern sort of flight director type variometers. They're linked up to your GPS. They've got all the information you need. Okay. This particular one, you can look at your average rates of climb. You can set the McCready value. It'll give you all your task information, and it gives you a flight director on the yellow-green push-pull bar. It will give you speed to fly, but more about that later. Because you're getting the information in terms of speed, you need an ASI in your cockpit which is working, and I'm sure you've all got one. And you'll also need, amongst other things, a crystal ball, because McCready relies on your judgment skills as a pilot to interpret the sky ahead. Okay, the better your judgment on reading the sky, the more accurately will be your McCready setting, and therefore the faster your cross-country speed will be. How else are you going to know the strength of the thermal ahead of you? We're also going to talk about the term tangent. Now, a tangent is a line perpendicular to any given radius that intersects the circumference at just one point. Now, here's the circumference, there's the radius, there's your tangent. Now, you're wondering where we're going with this. Let's superimpose a speed polar onto that diagram and then get rid of the circumference and radius. There's your tangent to your speed polar, and we can derive information from this. So now that we've set the sort of ground rules and the tools that you need, let's look at the aims of the presentation. You need to understand McCready, and this is what we're hopefully going to achieve by the end of it. But to understand McCready, you need to understand polar curves. To understand polar curves, we're going to look at speed versus rate of descent. We're going to look at weight and how it affects the polar curve. We're going to look at expected lift and the polar tangent. And we're going to look at wind components. That's headwind, tailwind components and the polar tangent. And we're going to learn how to read off the polar diagram the information that we need. We're also going to look at climb rates versus cross-country speeds, predicting thermal strengths. This is probably the most difficult part and the bit that needs most practice from you guys. We're going to look at flying through lift and sink and what we do when we find ourselves in lift and sink. And we're going to look at final glide calculations and how McCready can help us get the final glide right. So pressing on, let's remind ourselves of just a few sort of criteria. Angle of attack and lift ends up as a curve. Airspeed and lift, it's a curve. Airspeed and drag, when you add them all together, it's another curve. There's an ongoing theme here, isn't there? So when we get to things like the speed polar, it won't be surprising that it ends up being a curve. Okay. Now I've chosen, I've chosen the geodiscus simply because it's got a dynamic cockpit range, cockpit weight range, and it can carry water ballast. So it's a good example to study. I've chosen it because I've got a picture of it, a good one. I've chosen it because I've got access to the polar information, and you'll all recognize this from Condor. Okay. The numbers are quite accurate. I've also got access to the flight manual, and within the flight manual, we have a page which shows us the speed polar diagram. Let's stop on this slide for a few minutes and just discuss the speed polar. Along the horizontal axis, the x-axis, we have airspeed. I'll put 3 different nominations of speed up there in miles per hour, knots, and kilometers per hour, just for those that work in different sort of values. Up and down the y-axis, we have our vertical airspeed. And again, I've done it in knots, feet per minute, and meters per second. So it's a basic polar diagram. Within the confines of the polar diagram, we have 2 curves and 1 straight line, the straight line being the tangent that we looked at earlier. The dotted line of a curve, which is the lower of the 2 at this end and the higher of the 2 at that end, is the minimum weight that you would fly your glider at. In this instance, the geodiscus, 500 kgs, giving a wing loading of 30.5 kilograms per square meter. The solid curve is your maximum all-up weight. 700 kgs, 42.7 kilograms per square meter. At all times, you will be somewhere between those 2 lines. You will never be outside of those 2 curved lines when you're flying. Okay? That's your weight range of the aircraft. The tangent, as you'll notice, intersects both curves. It's not well defined in the manual, but it's only 1 point on both curves. And each intersection, one about there, one about there, there's about 10, 11 knots between them. It's not a great deal. But at the lighter end, your best glide is somewhere around about 51 knots, 52 knots. And at the heavy end, your best glide is around about 62, 63 knots. Are you all with me so far? You're happy with the information we've got there? If you want to read any information off the graph, it's like any other graph you've done at maths at school. Okay? Go along one axis until you find the value you wish, and let's take 150 kph. We'll come down 150 kph until we intersect one of the 2 curves, go across to the left, and that'll give you a rate of descent at that speed for that weight. All make sense? Cool. Alternatively, you can go down the, say, take 1.5 meters per second rate of descent, and you can see the speeds at which you can achieve that for the differing weights on the aircraft. We'll come back to that shortly, and we'll do some more sort of in-depth analysis of weights and speeds. So that's your basic polar that you'll find in your flight manual. I'm not going to refer back to this. I'm going to stick with the Condor 2 ones because they're actually clearer diagrams, and it's easier to explain using the Condor 2 diagrams. But before we get there, let's just have a look at the fixed and variable values that can affect the polar of a glider. So for any given wing profile, there will be a polar curve. Okay? And that's fixed. It's fixed by design, and it's set in fiberglass and resin. You can't change it. And I can already hear a few of you thinking, what about flat gliders? Well, for flat gliders, there's a range of polar curves for every flat position you have on your flat lever, or at least there should be in your flight manual. For all gliders, weight is a variable between minimum and maximum cockpit load. And for some gliders, weight is a variable depending on the water ballast you apply. And for all gliders, wet wings will alter the performance in a negative way. Okay? You've got water on the wing, it reduces the performance. Simple as that. Anything else that might reduce the performance? Speak up. Bugs. You're right with me there. Bugs. Anything else? More bugs. The more you fly, the longer you fly on a task, the more bugs you pick up, the worse your polar will get. Dirty wings, ice, all those kind of things, they all affect your polar. But it's more likely that on a cross-country task, bugs are going to be your biggest bugbear, if you excuse the pun. So let's press on. We're going to look at a geodiscus with one person on board, no water ballast, and we're going to see what the best glide is. Now you'll see up here, those that are familiar with Condor, we've not ticked the 2 pilot box, so we're just 1 pilot. There's no water ballast in the top box, everything else is 0, and the tangent intersects the polar and is telling us to fly at 50 knots. The rate of descent we'll achieve at 50 knots is 1.08 knots. So let's start writing a few of these things down just to make comparisons. So wing loading, we have 30.5 kilograms per meter square. So 30.5. Best glide, 50 knots. Rate of descent in knots, 1.08. And our LD ratio, which is shown here as E, this doesn't show up on the screen, but it's just underneath the dot there on the curve itself, 46.1 to 1. That's the thing that Condor doesn't show. It's 46.1 to 1. That's your lift drag ratio. And the way that's worked out is you take your 50 knots and you divide it by 1.08. It's simple. The answer is 46.1 to 1. So that's the glide angle you will achieve at minimum weight, effectively. So how about we put some tocking ballast in the back? We've now ticked the 2 pilot box. There's still no water ballast. Everything else is still 0. The tangent is still intersecting the speed polar at just 1 point. But the speed polar itself has moved. If you look at the 2 orange dotted lines, it was on the one top left. It's now moved down a bit because we're heavier. And we're now being told to fly, oh, sorry. That's when you push the wrong button. We're now being told to fly at 54 knots. Our wing loading, 35.4. .54 knots. Rate of descent, 1.17. And I don't need to look up there because I know it's 46.1 to 1. It's the same. Same LD ratio, same glide angle. Why? It's the same wing. We've not changed the shape of the wing. We've just made the glider heavier. We need to fly faster to get the same amount of performance out of the wing. Let's add some water ballast this time. 170 kgs of water ballast, 2 pilots on board with our maximum all-up weight, 45.7 kgs. That's our wing loading per square meter. And the tangent is now telling us to fly 61 knots. A rate of descent, 1.33 knots. But we're still achieving 46.1 to 1. Does that all make sense to you? Yeah? We're heavier, so we need to, yes. Wait on the microphone.
The wing shape stays the same, and what this is showing is there's a continuous, all throughout the flight regime, a continuous optimum angle of attack for the wing to operate at. My question is is as you increase the airspeed to allow this angle of attack to reduce to that optimum angle of attack, is there no effect from the parasitic drag from the fuselage on the lift to drag ratio?
It's minimal,
No.
such that you probably won't notice. But you're absolutely right. Okay, so we're happy here that changing weight means that we need to fly faster to get the same performance out of the glider. I'll just let this run. We'll look at all three and I'll just layer them up. The things to watch are how the weight changes in the top left-hand corner and how the polar moves down and to the right. Anyone like to see that again? No? Let's move on then. So, an easy concept to remember is we start at A, we glide to B, and we climb to C. So there's you're leaving your cloud base at A, you're gliding to the next thermal, which is B, and then you're going to climb up in that thermal to point C. Simple concept. We'll use that analogy throughout to describe what we're doing. Rhetorical question, and please don't shout out, keep the answers to yourself. Which is the most important? Is it A to B, B to C, or A to C? Well, we'll come back to that in a little while. What I'd like to do now is to look at setting McCready to a simple 1 knot. Now, the reason I've chosen 1 knot is because it gives a best glide of 60 knots. 60 knots makes the maths easy. It's a nautical mile a minute. When we do the maths, you know, it's easy to understand. Now, the first thing you notice here on the polar is that the tangent no longer originates along the x-axis at 0, or the y-axis at 0. It's actually originating from 1 knot on the y-axis, which is what we have set here as our McCready value. The other values, we're back to just 1 pilot, no water ballast on board, just to keep everything simple. And yeah, you're absolutely right there, Rainer. For some reason, the wing loading isn't correct. However, the rest of the numbers are correct. Yes, the water ballast, it is, yeah, the water ballast is up there for some reason. It should be down here. Anyway, the McCready value is set to 1, and it's telling us to fly at 60 knots here. And that is correct. Looking at it in the format that we've actually been looking at previously, we're just given the bottom right-hand corner of the polar. This is what it looks like. So, flying at 1 knot, flying at 60 knots with the McCready set to 1. What I'd like to do is to compare 2 pilots flying identical gliders at that speed. And this is where our disclaimer comes in. Pilot number 1, no resemblance to you, Alistair, it just happens to be the name I picked of the board, estimates the next climb to be 1 knot, because you've been flying in 1 knot thermals all day long. However, the next 3 thermals that you fly to are better than expected. There's a 2 knot, a 2 knot, and a 4 knot. So you decide to stop and climb in each of them. Sant, however, although he estimates the next thermal to be 1 knot, because he's been in 1 knot thermals all day, he's a wave pilot. And he misses the first 2 thermals and stumbles into the 4 knot thermal to prevent himself from landing out. Here's a pictorial representation of that. Alistair has flown from A to C via the top route of glide, climb, glide, climb, glide, climb. I've kept the numbers easy so that we can do the maths in our head. And he spent 27 minutes, 30 seconds flying 15 miles to get back to cloud base. Sant, on the other hand, has flown 15 nautical miles, taken one climb, and lo and behold, it's taken 22 minutes, 30 seconds, 5 minutes quicker. Do we understand that? Yeah? The thermal values are at the bottom here. Okay, 1 knot, 2 knot, 2 knot, 4 knot. So we've left a 1 knot thermal and we've timed it to the top of the 4 knot thermal 15 miles away. And that's the difference. Okay, that taking this, just the stronger thermal makes. So McCready says thermal strength is all important. Yeah. And for those of you who have chosen B to C as your answer, okay, don't shout out just yet. Just sit there in smug mode amongst your peers. Let's glide on to the next bit and analyze what actually went on here. What did they get right? What did they get wrong? So Alistair flew at 60 knots of the first thermal. Absolutely right. He chose McCready as 1 knot. That was his guess on the sky ahead. So he's flown at the right speed. McCready told him to fly at 60 knots. However, the first thermal he bumped into was 2 knots, so he stopped and took it. That's absolutely right. That's what you do when you're flying to McCready. Anything better than the expected value, you stop and take. However, he flew onto the second thermal at 60 knots, and he'd already been in a stronger thermal. He's still thinking it's a 1 knot thermal. So there's a mistake, and an easy mistake to make. Okay? If you set your McCready to a value and then think that that's going to do you for the rest of the day, there is your first mistake. So he stopped in the second thermal and he's climbed. That's exactly what's right to do. And even if it was, a far better thermal, it would still stop and climb. Oh, sorry, even if he'd set McCready to 2 knots, he'd still stop and climbed because it was equal to the McCready value. However, he's flown on to the third thermal at 60 knots. He's still on the 1 knot McCready. He's not changed it. But he has got the next bit right. He stopped and climbed in the 4 knot thermal because it was better than the predicted 1 knot. So overall, perhaps Alistair had failed to recognize the stronger lift ahead, and he's not reacted to the changing conditions. And bear in mind, he might have been airborne for 3 or 4 hours when this scenario happens. And he's been in 1 knot thermals all day long. Sant, on the other hand, missed both thermals. He got that wrong. He should have stopped and climbed on them if he found them. But he flew at 60 knots to the third thermal, and he'd only predicted 1 knot, so he's flying at the right speed, as per his choice of McCready. He stopped and climbed in that 4 knot thermal, which is correct. But he's also failed to recognize the changing conditions ahead and react to them. So overall, neither pilot predicted the 4 knot thermal, but why? Perhaps the queue down track looked exactly the same as that behind. Perhaps the earlier climbs of 1 knot had got them lulled into a false sense of security, and they'd gone, 1 knot will do me all day long. I'll fly at McCready for 1 knot. Perhaps they weren't looking far enough ahead down track before they climbed up. Okay? If you wait until you're at cloud base before you try and assess your next thermal, it doesn't work. You have to do it when you're low down. There's many other reasons. Okay, just to give you a little break from this, 30 seconds, I'll let you read this next slide on your own. 1 or 2 giggles. Some people can read upside down. Hooray for aerobatics, eh? So moving on, let's crunch the numbers for 4 gliders flying at different speeds. And your A, B, C concept is going to be 5,000 feet, 5 nautical miles, back to 5,000 feet. And we're going to do it in a 4-knot thermal. And we'll just crunch the numbers for that 4-knot thermal. So everybody's going to fly through exactly the same air mass, but they're going to do it at different speeds. Each glider identifies as, this is bringing us into the modern age of who's who. G-Mins is going to fly at 43 knots, which is minimum sink. G-Best is going to fly at 51 knots, which is best glide. So obviously from those figures, we're talking 1 pilot, no water ballast. G-Fast is going to fly at VA, which is 81 knots. 97 knots. And G-McCready is going to fly 81 knots, which is the McCready for an anticipated 4-knot climb. And that's straight from your polar and your tangent, with the tangent originating from 4 knots on the y-axis. What we're about to see is an animation depicting those glides. The timings are accurate. It's on a scale of 60 to 1. So for 1 second on the screen, it's 60 seconds in real life. And we're going to fly 5 nautical miles, and they're going to descend the appropriate height depending on the speed they're flying at. Here we go. Don't see that again? I'm sure you do. I certainly do. Let's do it with a bit of commentary this time. All 4 gliders start at the same time. Off they go. The first one to get to thermal is V-Fast, then McCready, then Best Glide, then Min-Sync. Okay. Just to drive this home, let's watch it again. Everybody happy with that? Cool. So now that we're there, we need to climb back to cloud base. Best Glide's got 657 feet. It takes 1 minute 36. Min-Sync, 722 feet, 1 minute 47 to climb back up. McCready, 961 feet, 2 minutes 22. And VA, flying at 91 knots, has 1,500 feet plus to climb, and it takes 3 minutes 52. So not only is it taking them differing times to get to the thermal, it's going to take them differing times to get back to cloud base. So here's our next animation. Okay. As McCready reaches 5,000 feet, after 6 minutes and 4 seconds, VA is not far behind, 51 seconds. Best Glide, 1 minute 32, and Min-Sync hasn't even reached the thermal yet when McCready gets to the top of the climb. Now, admittedly, it's only over 5 nautical miles, but still. Let's watch the animation this time. Again, it's 1 second on the screen for 1 minute in real time. And let's see who gets to the top of the climb first, okay? So the previous one was just looking at who gets to the thermal first. This is the full works. Shall we watch that again? I quite like that. Shall we? Even if you don't want to watch that again, I'm going to play it again anyway. Okay. VA is there first, McCready second, but McCready's climbing above VA. Then Best Glide, then Min-Sync. Min-Sync's the last one to the top of the climb. Does that all make sense? Yeah. I think that's a far better way of looking at McCready than sitting and doing the maths. But to do that, I had to do the maths to put it into the computer to find out how to display it. So McCready says speed to fly is all important. And those of you who thought A to B was the right answer, just switch on smug mode and sit quietly. Okay, so let's just have a quick look at McCready speeds and or McCready values and speeds to fly. Here we're selecting, I know it says 2.1 knots, but roughly 2 knots. Condor wouldn't let me select 2 knots exactly, so I've done the 2.1 knots. That's telling us to fly 84 knots. Rate of descent is 2.19. It's given us a glide ratio of 38.3 to 1. And just to show you that the tangent does go to 2.1 knots, that's it described there. Let's up it from 2.1 to 4.1 knots, or roughly 4 knots. It's now telling us to fly 96 knots. Christ, this is getting fast, isn't it? Yes.
Answering your question, that's the polar curve based on the airfoil only, or is it based on the whole aircraft?
What
The actual polar curve?
The polar is based on the wing profile.
Is it, there's only aerofoil profile.
But it does relate to the aircraft's performance. In the flight manual, the polar is measured actually on a flight test.
Yeah, that's what I was asking. Yeah,
so absolutely, yes.
So parasitic drag with increasing speed will be included in the shape of that polar curve. So that's compensated for the.
Yeah.
Cool.
Absolutely. Thanks, Max. So where did we get to? We've upped McCready to 4.1 knots here, and it's telling us to fly at 96. And let's just go one more step. We've upped it to 6 knots, and it's telling us to fly at 101 knots. Oh, this is getting really fast. You know, the leading edges will be getting hot now. So thermal strength and speed to fly are all important. Okay, and those that chose A to C, well, give yourselves a pat on the back. Well done. So gliding on to the next part. McCready is primarily all about guessing the next thermal strength and then gliding at the optimum speed to reach the climb at a height which will allow you to arrive at cloud base quickest. Go with me? Good. Now, you could use your crystal ball, if you've got one, combined with your judgment skills, or you could use the electronics that you've got with you. And that's probably the more sort of preferential choice these days, is to use your instruments. So to fly McCready, you need to know your instrumentation. So how do we actually choose what McCready setting we're going to use? This is my method. You can choose your own method. Okay, I'm not saying this is the finite way or the only way to do it. I look at the last 3 thermals I've been in. I also look at the sky ahead, and then I make a choice. So let's say the last 3 thermals I've been in are all 4 knots. And the sky ahead looks exactly like the sky behind me. It goes without saying I'm going to choose 4 knots as my McCready setting. It's as simple as that. Okay. Know the sky you've been flying in, look at the sky ahead, make your comparison, choose your value. So let's hazard a guess at your rate of climb here. Thor, how fast are we climbing here? Fantastic. However, that's an instantaneous value. Anybody else like to hazard a guess at how fast we're climbing here?
About 5 knots.
About 5 knots. Why would you say 5 knots, Richard?
Well, if that's the instantaneous, we're in and out, it's thermal, then I would say it's probably half of what you're registering instantaneous.
Okay. That's not bad. That's not a bad way of working. I quite like that. However, it does it for you here. Averager, 4 knots. Okay. You can select the time span that your averager will work over, be it 10 seconds, 20 seconds, 30 seconds, so on and so forth. I personally use a 30-second averager. It's just something I enjoy working with, the last 30 seconds. And here, yeah, absolutely. So here we're actually climbing not at 8 to 9 knots, as the instantaneous value tells us. We're actually climbing at 4 knots. And that's the figure that counts. That's the one that you need to use for McCready. You have an you have an indicated climb of any given moment in time, and you have an average rate of climb, okay, which is the one that the maths works for. So when we're talking about climb, we need to talk in terms of average rates of climb and not instantaneous. Through that door in the bar, you will hear lots and lots of stories of, oh, I was climbing at 10, 12 knots, when really they're only climbing at maybe 5 or 6 knots. Okay. It's the 5 or 6 knots that's the important one. That you put that into McCready and that'll get you around the task the fastest. Now, I understand, Sant, that you've now gone out and bought an averager. So it's just my sense of humor. So moving on, let's talk about headwind, tailwind component. Here on the diagram, we've put everything back to 0 weight, 1 pilot. However, we've got a wind speed of -27 knots. I've taken it to extremes to make it easy to visualize, because after this one, we're going to look at +27 knots. That's the maximum that Condor would allow me to go to. Wind speed of 27 knots. Have a look where the tangent intersects the x-axis. Smack on 27. Okay. Again, it's giving us 62 knots to fly at, and we're coming down at 1.48 knots. Now, if you divide 62 by 1.48, you certainly don't get 23.6, which is what the glide angle is telling us. However, if you take 62 knots and subtract 27 from it, and then divide the resultant by 1.48, so it will give you a glide angle of 23.6. Okay, so this is how we work out your glide ratio going into wind. It will become very easy to spot when we go into the tailwind. Okay, +27 knots over here. It's telling us to fly at 47 knots here, but look at the glide angle, 71.7. You have to be going downwind, achieving that glide angle, 71.7 to 1. Okay, with a stonking tailwind. Okay, so that's how you can work out your glide angles and speeds to fly in headwinds and tailwinds. The modern state of affair is that your electronic vario will do that for you, especially when it's connected to GPS. It will work all this out for you. You don't even have to worry about what the wind's doing. It will tell you. So let's press on. Variometers. Think of it as a flow meter. Okay. All it's doing is measuring the rate of flow of air into or out of a flask, a capacity. It could be a bottle. Okay. We tend to use, in the olden days, thermos flasks, because they thought that the temperature wouldn't change too much, or it wouldn't be affected by temperature change. So, as we climb, air pressure reduces, creates an imbalance in the system, and air flows out of the flask through the variometer, giving an up indication. As we descend, pressure increases, imbalance in the system, air flows back in. Okay. So if your vario is going up or down, it will read up or down. And you might think, oh, that's fine. We've got a nice system here. But we don't. There's a thing called stick lift. And that essentially is, if you're flying along and you intentionally slow down, the glider will climb. Of course, your vario is now going up. So your vario will indicate up. But do you really want to know from your vario that you're going up? Not really. You've already moved the stick back. You know already you're going up. You don't want to know what the glider's doing. You know that already. You want to know what the air mass roundabout is doing. So let's introduce the total energy tube. At this end, at the tip of the total energy tube, I've amplified it into the sort of grey circle there and shown the total energy tube with 2 holes drilled in it. The size of the tube and the size of the holes all go towards a sort of calibrated system where when air flows around that tube, it will suck air out of the system to a certain extent. So,
also the distance from the holes to the tip of the tube is decisive.
absolutely, yeah. So it's also known as a Brunswick tube. And how does it work? Well, it creates a low pressure system in the lee of the tube. That sucks air out of the system, but only until it reaches a balance point. And once that balance point has been reached, it will sit there quite happily all day long. However, as we climb a descent, the same will happen. Air will flow out, it will flow in. But as we speed up and as we slow down, it'll affect that little low pressure behind the tube. So the low pressure deepens with increasing speed, sucking air out, and that cancels out the flow in due to the increase or the rate of descent increase with the increase in speed. It's a very, very basic, but very, very ingenious method of calibrating your system, isn't it? We all understand the concept. Okay. Let's move on. Now we know what the air mass is doing. We can slow down and speed up in the lift and sink, because the longer you spend in lift, or as some pilots like to call it, energy, the longer you spend in that energy, the further you will go. The less time you spend in the sinking air, the further you will go. So, moving on to how do we decide speeds to fly using the old method, McCready ring here. You'll see at the top, on the end of this red arrow, a little triangle, and we've set that to 4 knots. I've chosen 4 knots as kind of a recurring theme throughout the presentation. So we've set McCready to 4 knots, and when we're flying through rising air, descending air, whatnot, our vario is going to be telling us it's rising and descending air because we've got a totally compensated system using a Brunswick tube or a total energy tube. And wherever that needle points, and here it's pointing at 3 down, but it's also pointing on the McCready ring at 105. That's telling us to fly at 105 knots. And if we fly into rising air, that vario is going to move up. And that's telling us to slow down. If you follow the speed on the McCready ring, that will tell you what speed to fly. Now, I'm not saying that you sit with your head in the cockpit, watching it intensely and following it, but use it as a guide. Okay, you need to keep your head out of the cockpit for a good look at. But this is how we use the McCready ring. We set the value of our next expected climb, and then we follow the needle, reading off the speeds, and we apply those speeds to our ASI, and that gets us flying at the right speed. Okay, so there's our speed to fly. We're all happy with that? The modern version tends to be where we've got the V and the S there. We've got cruise climb or climb cruise as I've got them orientated on the screen. And then your flight director is telling you whether you're too slow, whether you're too fast, or whether the speed's just right. But it's the same thing, exactly the same thing. It's your needle following the McCready ring, just in an electronic format. It's nothing to be intimidated by. However, you do need to learn how to use your instruments to be able to follow McCready. So, put this into practice. Tactics of flying McCready. Looking at dolphin flying in favourable conditions. Now, for those of you who have done lots of cross-country flying in thermals, you will recognise this as being somewhere south of the border. Yeah. Yeah. 3-4 knot thermals in a row. Is that going to happen? Well, hopefully it will next season. But essentially what we're doing here is we're climbing up to cloud base, we're leaving to go off on a glide, and we've given ourselves a working height band. I put my personal limits up there when I'm flying something like a K21 on an actual cross country. I will fly McCready down to about 3,000 feet. Once I'm below 3,000 feet, I'll be a bit more conservative. And once I'm below 2,000 feet, I'll go into survival mode. There's nothing worse than de-rigging a K21 in a field. Absolutely, yeah. So it's glide, it's pull up in the lift, it's press on, it's pull up in the lift, it's press on. It's, oh, this one's not quite so strong, but I think I can probably get to the next one before I'm down to my sort of lower heights in my operating height band. And then you hit a good climb, and you take that climb, and you're back up to cloud base, and you carry on all day long. And if you can do sort of 5 or 10 of those repetitions on a flight, you're going to be romping home and having a great time. It doesn't always work like that, though. Less favourable conditions. You might set off at McCready speed. Yes, Tor.
In regards to the last slide with the height bands, is it worthwhile as the lift you're getting from a thermal tapers off the higher up the thermal you are? Is it worthwhile when you've got pretty favourable conditions, setting off a higher height band rather than climbing all the way to cloud base and like lift tapering off down to from 4 knots down to a lesser? Right.
That is a very good point, a very valid point, and I'm about to cover it in a few minutes. But as a brief answer, yes, it is worthwhile bringing that height band down. So we've missed the next thermal. The bubble's gone. We glide underneath it. We curse and swear, and we slow down a bit below 3,000 feet. We get down to 2,000. We slow down even more. We go into survival mode. Okay, we reach a weak climb. We take it. We're in survival mode. Okay, we can't afford to press on to the next thermal. Okay, we take that as high as we need to get to a better climb. We glide onto that better climb, and we take it back to cloud base. And off we go again at McCready speed. So tactics of flying in less favorable conditions. We're just about to discuss the point that Thor was trying to make here. Rejecting lift. Yeah. When would you reject lift? Okay. If you're not a cross-country pilot, probably never. Okay. You will be loath to leave your climb to move on to the next one. But for those that are serious about going cross-country, you want to reject the lift when the climb rate deteriorates and there is better looking lift around, okay, within gliding range. Okay. Okay. If you think there's something better, what are you doing here? Go there. Okay. Go to the better climb. Okay. The other time to reject lift is when your final glide height is reached, including the safety. Okay. Yeah, absolutely. Yeah. I'm going to do final glides in a minute. So once you've got your safety height, okay, off you go. That's the time to press on. Okay. Don't wait there to cloud base. You will get back slower, not quicker. When to dolphin. So when you're within your operating height band, okay, and the or on the final glide, and the lift is less than or equal to McCready, slow down through the lift, press on. Do not stop and climb. And when to stop and climb, at any time during the flight at all, if you encounter a climb which is greater than your anticipated McCready, stop and take it. Okay, that is going to improve your cross-country speed, no end. Okay. Also, when the climb rate is equal to McCready and you're close to the lower part of your height band, stop and climb. You might not get to the next one, okay, before you exit the bottom of your height band and have to slow down and go into sort of survival mode. And of course, when flying below your operating height band, if there's nothing better within climbing range, stop and take it. Keep yourself airborne. Okay? Don't press on to something you think is better and end up landing out. Okay? So have that little gear shift change up here. Okay? Decide when to reject lift and press on, when to dolphin, and when to stop and climb. Okay? 3 very, very, very important factors in flying cross-country. Let's take you back to the concept of gliding A to B to C, but let's turn that around a little bit. Okay. We're now looking at final glides. The stronger the climb, the higher we can go, the faster we can get home. Okay. McCready will tell you how high and how fast to fly. So we start at A, we're climbing towards cloud base, and at some point we will reach B, which is the earliest time we can glide home. Best glide. Okay. You will not get home leaving lower by flying at any speed you like. You have to go to that height to get home at best glide. So I've taken figures from the flight manual this time because I don't want to put McCready figures out into the domain where you might end up flying these things. Best LD, 45 to 1 at 55 knots with 114 feet per minute rate of descent. That's from the flight manual. So let's look at 20 nautical miles as a final glide. We can do the maths here. Time equals distance upon speed. 20 upon 55 gives us 21 minutes and 48 seconds to cover that distance. If we're going to spend that amount of time flying at a rate of descent of 114 feet per minute, we need 2,487 feet to achieve it. That's with no safety, absolutely none at all. Okay. You might even need to keep your undercarriage up until you cross the hedge. Okay. No safety at all. It's the absolute minimum required in still air. However, we don't climb in still air, do we? We're going to be climbing in a thermal before we set off from the glide. So we're not going to leave at best glide. Okay. Here's our trusty 4-knot thermal again. How high do we go and how fast do we glide home? Okay, so like in the previous example, we need to know the best LD. If we look up 4 knots on our McCready or our polar curve, sorry, you'll find that, again, from the flight manual, 31.5 to 1 at 81 knots, 256 feet per minute rate of descent. And if we do the maths, the numbers are scrolling up the screen there. 20 nautical miles, we'll cover that in 14 minutes and 49 seconds. Okay. Height required, 3,792 feet this time to get back at 81 knots. Total time of 18 minutes and 4 seconds. Okay. The previous one was 21 minutes and some seconds, wasn't it? So by going higher, okay, and flying faster, we can get home quicker. 3 minutes, 44 seconds quicker. Okay. And again, I'll stress that that's the absolute minimum height required to get home. You will need safety height on top of that, obviously. And when you're doing final glides these days, you're probably gliding back to a finish line, which has a minimum height of 300-400 feet anyway. So you need to factor in those figures. So McCready says the thermal strength of the last climb dictates the height to start and the speed to fly on your final glide. However, in reality, when you're flying something like a geodiscus, you're not going to wait until you're 20 miles away before you start your final glide. Okay. And certainly in the competition, you're going to try and leave a bit early, as soon as you can on the final glide. So here's some figures just for interest's sake, really, of, say, a 40 nautical mile final glide. There's the figures. It's going to take us just under half an hour. You're going to need just over 7,500 feet, but glide base is 5,000. So you're going to have to dolphin fly to get back. You're going to have to follow the energy. And here's the tactics of that kind of flight. You've got lots of English thermals lined up, and off you go. Glide, pull up, glide, pull up, glide, pull up. And eventually you find yourself above the glide. Okay? Don't relax at that point, because you can end up back below the glide again, okay, if you don't get it right. You must follow the energy all the way home. Okay? That's what McCready is all about. It's about following the energy. So those were the aims of the presentation. I think we've had a look at speed versus rate of descent. We've certainly had a look at weights in the polar curve and how weight affects the polar curve and where it moves on the graph. We've had a look at expected lift in the polar tangent, how the origin of the tangent moves up and down the vertical axis, and we can read off the different speeds for the different expected lift that we're plumbing in. We've had a look at headwind and tailwind components in the polar tangent. We've discussed climb rates and cross-country speeds. The better the climb, the faster you will fly cross country. It's not rocket science, it really isn't. We've had a look at predicting thermal strengths. Probably the most difficult part of flying McCready is your understanding of the weather and being able to read the sky ahead. We've had a look at flying through lift and sink and what to do. Slow down in the lift, speed up in the sink. Again, not difficult. And we've had a look at final glide calculations and how you can get home quickest. So, in conclusion, to fly McCready accurately needs good knowledge of the weather in order to predict your thermal strengths accurately. To achieve high cross-country speeds, you have to follow the energy. McCready speeds are still mathematically proven speeds to fly. So follow the indicated speeds given by the flight director. But do it with a pinch of salt, I would say. Keep your head out the cockpit. Don't just stare at the instrument and try and follow it religiously. Look out, look at the sky, follow the energy. If your thermal strength is stronger than chosen McCready, stop and climb. I can't emphasize that enough. That one thing is a really good strong climb. You pull up in it, you're 500 feet below cloud base. Oh, I won't bother, I'll push on. No, stop and climb. Take one turn to get you to cloud base and press on. You will be quicker on the task for doing so. Considering increasing your McCready setting if you encounter lift like so. And remember that rejection of poor lift is equally as important. Okay? Don't hang around in 2 knots when there's 4 knots around or 6 knots around. Okay? Get to that 4 knots, get to that 6 knots, make use of it. And of course, remember to set McCready to the last thermal strength for your final glide. Okay? You're not looking at the next thermal strength, you're looking at your previous one now. You've turned the thing around. Okay? Don't set off until you're above glide unless you're confident that you can dolphin your way onto glide and follow the energy on your way home. One of my biggest mistakes in early years was, I'm on glide, relax, off we go. Oh shit, I'm below glide. Excuse my language. Okay. Follow the energy on the way home. Final glide is not a straight line. Okay? It's like every other part of your cross-country flight. Follow the energy. So here's a little fact for you. Anyone claiming that they've flown better than McCready clearly underestimated the sky ahead. I've done the maths. What they really meant to say in the conversation was that they were actually flying closer to McCready than they had thought. And when you do the maths, that's probably quite a true statement. A little something for you to think about, not related to McCready, but it's a mindset thing. When you're flying in cloud, no matter what your brain's telling you, believe your instruments. So why not when you're flying McCready, no matter what your brain's telling you, believe the maths. Okay? Fly McCready as close as you can, and you will get there. Gratuitous gliding picture to finish the evening. If you've got any questions, I'll take them now. And in the meantime, I'm sure Martin's got the bar open. Thank you very much. Okay, any questions? Truth, I must have covered it all. Yes, Ryan.
One thing, when you dolphin and you say follow the McCready speeds, there is a little bit of time lapse in the indication of the ASI.
Yes.
And also if you have high jumps in the speed because you go through rather turbulent thermals, don't follow exactly the speeds. You
No.
will, with every move of any rudder, you will increase drag.
Absolutely, yeah.
So just take it very lightly. Fly
Yeah.
with your fingertips.
Absolutely, yeah. A point that John and I were discussing earlier was flying block speeds rather than accurate McCready speeds. What Johnny was suggesting, and I think you're about to do that right now, are you?
Kind of. It was kind of to go along Reiner's point of a practical example of that is when you watch a training aircraft do that, exactly that, follow the speed. They're going like this, up and down, up and down, up and down. We're wasting a lot of time in speed, whereas there's a group of about 2 or 3 of us, like all just kind of pushing through the lift and speeding up. Maybe one of us would say, okay, put the McCready up 0.5 of a knot, and we'd all just start flying a little bit faster through the lift, and it kind of it takes away that kind of all the drag you're creating through moving controls. And then with flying block speeds, we were saying that it brings you close enough to the McCready without having to sit and stare at your instruments and kind of think, okay, well, I have to fly at this exact speed, because I've met a few people that pick that apart to the nth degree, and funnily enough, they're getting beaten by juniors that are just flying block speeds and kind of going, oh, that looks fine, go for it. Because it's part of it is also by flying by feel and kind of.
Yeah, absolutely. I would totally agree with that. McCready is a theoretical system which, if employed, can be of great use to you. But if you're not capable of flying absolutely accurately without creating any drag, and following that energy and anticipating the lag in the vario and pulling up that little bit, half a second earlier than the vario's telling you, etc., etc., then yeah, flying block speeds is a good thing to do. Yes, Richard.
I think as part of that as well, when you're dolphining and or if you're thermaling and you're wanting to anticipate coming out of a thermal at cloud base, a great deal of speed can be gained by speeding up in the top of the thermal before you exit and getting into the lift. It's that fine line between hanging around at
absolutely,
47 knots in a 5-knot thermal and then speeding up to get through the next piece of lift. And it's quite important, halfway around the last turn, to really start increasing your speed to push forward and then head for your next thermal.
Absolutely.
A lot of times last I used to do it, waft around, get to cloud base and think, oh, I'll bimble now.
Yeah.
And then push my speed.
Although I would class that more in thermaling technique.
Yeah.
I would say, yes, it is relevant to flying McCready. You do need to look at your speeds around the last half of the turn of your thermal so that you're up to speed to fly out through the sink. So yeah, you're absolutely right. Yes, Tom.
For final glide, you're talking about calculating your McCready, what height you should start off and what your average speed should be for final glide, assuming it's still atmosphere. If the start gate, if the finish gate, sorry, was a safe height above the ground, sort of 1,500 feet, whatever, so terrain isn't an issue, would it be an idea to do your final glide with the McCready aiming for the lower half of it or even below it, so you can use your energy afterwards to pull up so you can get a higher average speed over that descent?
It would depend. If you're flying a competition, for instance, it would depend on the competition rules as to whether you could cross the finish line coming up through a height limit or going down through a height limit. And I would suggest that most competitions, or if not all competitions, you're descending down through a level. And what you want to do is when you reach the vertical limit and the horizontal limit, you want to be clipping that corner if you want to do it at the absolute ultimate for fastest speed. So you final glide to that point and you put that point in to your GPS as your reference for the finish line, and you glide to that point at that height, and that will optimize your speed. Does that answer your question?
Yes, thank you.
Cool. Anybody else? Okay. Oh. Yep. Yes, Stuart.
It just came up from one of the pictures you had there. Which way up are you supposed to put a total energy sensor? Is it pointing down or pointing up? I've seen it so different all over different places. What's the right way and why?
I would imagine that we'll go with the we'll go with the majority here. Yeah, we'll go with the majority here. Most gliders have them pointing down. However, I would refer to the flight manual and see if there is a specific reason. Yeah, to see if there is a specific way that Brunswick tube or total energy tube should be pointing. Now, if you look at the ones that come up out the fuselage, quite often they come up and they're bent back a little bit to give the right orientation to the airflow for the sort of angle of incidence of the aircraft through the air. So there will be, you're absolutely right. And I can't answer your question right now as to any particular glider type. But I would say, yeah, read the manual, see if there's anything in there. And if not, then come back to me and we'll try and chase it up and then investigate it. Yeah, it might be as simple as that. Yeah, thanks, Max. I didn't think of that.
That was not all I've taken there, so
Not a problem. Right, if there's no other questions then, to the bar.